We will create the rendering functionalities in renderer's headers file, so let's start by including it in the app header file. Then go to the private section of the class, and after window visible, declare a shared pointer of renderer. Open app CPP. In the constructor, initialize the renderer as a null pointer. In the run function, call renderer reset commands. Now, create a code section for calling setRenderTargets and present. Let's create a lambda function at the beginning of run to handle the destruction of the application resources. Only call renderer_destroy for now, and execute it after the event loop. We copied this line for processing the Windows events at the end of the setWindow function. Now we create the renderer using std_make_shared and call renderer_initialize, passing core window get for current thread as a parameter. After initialize, call reset commands and close commands on flush to close and execute the GPO commands. We will handle the resize events by first asking if the renderer is not a null pointer, and in that case, we call renderer resize, sending the new dimensions of the window containing sender bounds. Copy and paste the width, and pass also the window's height. Now open the folder view, add a new folder named renderer, add to this folder a renderer header and a renderer CPP file. Go back to the solution view and add these files to the project as existing files. Add pragma ones. Use the namespace Microsoft URL, the namespace Windows UI Core, Windows Foundation, Windows Graphic Display, Platform, and DirectX. Let's create a rendered struct. Define static const UEntFrameCount as 3. Declare an agile core window as window. A com pointer to ed3ed12 device 2 as ed3 device. A com pointer to ed312 command queue. Name it command queue. Another com pointer to edxGUI swap chain 4 for the swap chain. A com pointer to ed312 descriptor heap for the descriptor heap of the render target view. An unsigned int to store the size of the render target view's descriptor heap. A new ed312 descriptor heap for the descriptor of the depth stencil view. An array of com pointers to ed312 command allocator for each frame count. Another for ed312 graphics command list 2. Declare a fence as a com pointer of ed312 fence. An unsigned int 64 to store the value of the fence. An array of unsigned int 64 for the values of the fence for each frame. A handle for the event handling of the fence. Declare a d3d12 viewport to define the viewport of the rendering, and a d3d12 rect for the scissor rect. Declare an array of ed312 resource com pointers for the render targets, another one for the depth stencil, and declare an unsigned int for the index of the back buffer. Declare an initialize method with core window as a parameter, a destroy method, an update viewport perspective method, a resize method with width and height as the parameters, a reset commands method, close commands on flash, another method named setRenderTargets, and a present method. In renderer CPP, we begin by including the precompiled headers, renderer, DirectX helper, device utils, and declare the usage of the namespace Windows Graphics Display. Go back to renderer header file and use the Visual Studio refactoring tools to define the renderer's methods. To test the compilation, let's comment the device utils include line, go to the PCH and change DXGUI14416, compile, and if you run the application, you should see a window without changes. In renderer initialize, assign the core window to window. And if we are in debug mode, create a debug controller using the function d312 getDebugInterface. Call enable debug layer to enable the debug layer. Then obtain a EDXGUI adapter 4 through getAdapter and uncomment include device utils. Create a D3D device using createDevice and passing the adapter as a parameter. Create the command queue with createCommandQ and pass the device. The swap chain is created by calling createSwapChain, passing the window, the command queue, and the number of frames. From the swap chain, obtain the index of the current back buffer. Create the RTV descriptor heap using createDescriptor heap, passing the device and the number of frames in the back buffer. We can obtain the size of the heap with getDescriptorHandleIncrementSize from the device, passing the RTV type as an argument. In the same way, create a descriptor heap for the depth stencil, passing one frame and the DSV heap type. Assign a name to the device, to the command queue, to the RTV descriptor heap, and to the DSV descriptor heap. Update the render targets by calling update render target views, passing the device, the swap chain, the descriptor heap, the targets, and the number of frames in the back buffer. For the depth stencil view, we call update depth stencil view, passing the device, the descriptor heap, the depth stencil resource, and the dimensions of the window. For each frame of the back buffer, we create a command allocator with the function createCommandAllocator. Then assign a name to it with setName and the index of the corresponding back buffer. We create a command list using createCommandList, passing the device and the command allocator currently assigned by the back buffer. Then give a name to the command list with the macro name d312 object. We create a fence using createFence, the fence event calling createEventHandle, then update the viewport properties by calling updateViewportPerspective. In the rendererDestroy method, we release every resource which has been taken by the application through Direct3D. Add string to PCH to enable std widestring. In renderer update viewport perspective, calculate the aspect ratio, dividing the width to the height of the window. Also define the scissor rect from the coordinates 0, 0 to the width and height of the window. With the same attributes, create the viewport but passing 0 as the near plane and 1 as the far plane. In the resize method, we execute the GPU commands by calling flash, passing arguments like the command queue, the fence value, and the handler which handles the fence events. Then iterate each frame of the back buffer, and in each render target, call reset and propagate the values of the current frame fence to the rest of the frames. Declare a swap chain desk and obtain its value with swap chain getDesk. Then call swap chain resize buffers, passing the number of frames in the back buffer, the new width, the new height, the format of the swap chain buffer, and the flags of the swap chain. Obtain the index of the current back buffer by calling swap chain getCurrentBackBufferIndex. and update the render target by calling update render target views, passing the device, the swap chain, the descriptor heap, the render targets, and the number of frames in the back buffer. Do a reset on the depth stencil resource, and call update depth stencil view, passing the device, the descriptor heap of the depth stencil resource, and the new dimensions of the window. For then calling update viewport perspective. In reset commands, first we get the current back buffer command allocator. For this command allocator, we call reset, and then we call the reset method on the command list, passing the commands allocator pointer and null pointer as a parameter. Let's leave close commands and flash for the end. And in set render targets, obtain the back buffer from the render target using the index of the current back buffer. On this back buffer, we will create a transition barrier from the present state to the render target state, so it can be pushed into the command list. We also push the assignment of the viewport and the scissor rect. We build a CPU descriptor handle from the descriptor heap with the function getCPUDescriptorHandle for heap start, and we will pass the index of the back buffer as offset and the descriptor size of the descriptor, which allows to clean the render target calling clear render target view, for which we will pass the predefined color cornflower blue. We create a CPU descriptor handle for the depth stencil, and clean the depth stencil with the depth flag and the value 1, without stencil and rects. And queue the render target assignment with omSetRenderTargets, passing one render target, a pointer to the CPU descriptor handle of the back buffer, false, and a pointer to the CPU descriptor handle of the depth stencil. In the present function, obtain the back buffer of the current frame, and create a transition barrier for the back buffer from the render target state to the present state. Queue this barrier onto the command list, then close it, calling command list closed. Declare an array of ed312 command list pointer to put the pointer to the command list as an element, and call command q execute command list using this array. Now call swapchain present, copy the fence value for this back buffer index to the fence value generated for this frame with the signal function, obtain the new index of the back buffer, and wait for the value assigned in a previous frame which used the value of this back buffer with the function waitForFenceValue. In close commands and flash, close the command list and execute it as it was done in the present function. And call flash, which will generate a new fence value and will wait for its execution. Now we go back to the folder view and add both deviceUtilsH and deviceUtilsCpp to the render folder. Go back to the solution view and add these files to the project. In deviceUtils, declare pragma1s, add the same namespaces from renderH, declare getAdapter, which will create a Directory12 adapter, create device for creating the Directory12 device, create command queue to create a command queue on the device we're passing, create swap chain for creating a swap chain for the window with the given number of back buffers, create descriptor heap, which creates a number of descriptor heaps for the given type on the device, update render target views, which obtains the back buffers from the swap chain and creates render targets for each one of these back buffers. Update depth stencil view to create a depth texture so it can be used as the depth stencil view. Create command allocator to create a command allocator on the device. Create command list to create a command list on the device. Create fence, which creates a fence for the device. The create event handle will create a handle for managing the events from the fence. The signal function, which updates the fence value and will queue this new value into the command queue. The waitForFenceValue, which waits for the fence value from the GPU. The flash function, which executes and waits for the completion of the commands on the GPU. Now let's use again refactoring tools to create definitions for the functions. In the CPP file, include the PCH header file, DirectX helper. In getAdapter, declare a edxGUI factory4 COM pointer. Then declare flags for the device creation. When compiling in debug mode, assign DXGUI create factory debug to the flag and use this variable to call create DXGUI factory2, passing create factory flag and the IID args of the DXGUI factory pointer. Declare a DXGUI adapter 1, a DXGUI adapter 4, a size t for obtaining the amount of available memory in the adapter, iterate over the factory's adapters, and obtain the adapter's description using getDesc1. If it's not a software adapter, it allows to create a level 12.1 type device, and the available memory is higher than the one already selected. Store the amount of memory from the adapter, convert adapter 1 to adapter 4, and return it at the end of the function. In the createDevice function, we will create a 12.1 device type using the adapter given as a parameter. When compiling in debug, declare a COM pointer to a ed312 info queue, which will be obtained from the device already created. We will tell to the info queue to interrupt the execution in corruption, errors, and warning cases. We'll ignore the info severity messages and ignore the clear value mismatch and map with null range messages. With this data, fill the filter structure of pinfoqueue and push it to the filter storage of pinfoqueue, and return the device at the end of the function. In the create command queue function, declare a direct3d12 command queue desk, where we assign list direct as type, normal priority, none as flag, and 0 as node mask. Create a command queue calling device create command queue, passing the descriptor to the command queue and IID args of the command queue, and return it at the end of the function. In the create swap chain function, we declare a DXGUI swap chain 4, a DXGUI factory 4, and the factory creation flags. To this flag, we will assign create factory debug into debug compilation mode. We call create DXGUI factory 2, passing the flags and IID args of the address of DXGUI factory 4. We create a swap chain descriptor to which we pass the width and height of the window. We will give it the R8, G8, B8, A8 unorm format without stereo, a 1-0 sample desk, a render target output buffer usage, the number of frames, stretch scaling mode, flip discard as swap effect, and unspecified alpha mode, and 0 as flags. Now we declare a swap chain 1 and call DXGUI factory 4 create swap chain for core window, sending as parameter the command queue a interpret cast of the window, the descriptor of the swap chain, null pointer, and the address of the swap chain 1. Then we cast the swap chain as swap chain 4 and return this swap chain 4. In the create descriptor heap function, we create a D3D12 descriptor heap desk, and we initialize it with the number of descriptors, the descriptor heap type, and heap flag noun flag. To create the heap, we use the device method createDescriptorHeap, passing the descriptor and a pointer to the heap, and return the pointer to the descriptor heap. In the update render target views function, we first obtain the size of the descriptor heap with the device method getDescriptorHandleIncrementSize, passing RTV as type. We create a CPU descriptor handle using the descriptor heaps method getCPUDescriptorHandle for heap start. We iterate over the back buffers, declare a pointer to a D3D12 resource for the back buffer, and we obtain it using the swapchain getBuffer method. We create the render target view with the device method createRenderTargetView, passing the back buffer, null pointer, and the CPU descriptor handle. We assign the back buffer to the render target with the index of the iterator, and offset the handle using the descriptor size. Let's fix this missing parenthesis. In the update depth stencil view function, we create a D3D12 clear value with D32 float format and 10 for the depth and stencil values. We call the device method create commit resource, pass a heap property of default type, heap flag none, a texture 2D resource desk of D32 float format and the same dimensions as the window, which allows depth stencil, the initial state of depth guide, a pointer to the clear value, and a pointer to the depth stencil resource. Name the resource, and create a depth stencil view descriptor and initialize it with D32 float format, view dimensions as DSV dimensions texture 2D, bib slice as 0, flag as DSP flag none. To finally call the device method create depth stencil view, passing the depth stencil resource, the descriptor view, and a handle to the descriptor heap using the function getCPU descriptor handle for heap start. The create command allocator function will call the device method create command allocator, passing the argument list direct as a command list type and the address of the com pointer of the command allocator, and we return it at the end of the function. In the create command list function, we create a command list with the create command list method of the device, passing 0, the command list type direct, the command allocator, a null pointer, and the address of the command list com pointer. We close the command list and return this com pointer. In the create fence function, we call device create fence, passing 0 as its initial value, fence flag none as flag, and the IID PPV args of the address of the fence com pointer. We return this fence. In the create event handle function, we create a fence event by calling create event. If the fence event is a null pointer, we throw an error by using the Windows function getLastError, and we can return the fence event. In the signal function, we increase the value of the fence. Add the signal to the command queue, passing the fence and this new value, which gets returned at the end of the function. In the wait for fence value function, first we ask if the current value of the fence is less than the value we are passing. And if it is, we call fence set event on completion, passing this value and the fence event handle. For then calling wait for single object with the fence event and an infinite waiting time. In the flash function, we get the fence value for the signal calling the signal function, passing the command queue, the fence, and the fence value. And we call wait for fence value with this value of the fence. Now go back to the run function in appcvp, and before calling destroy, we will call flash, passing the next rendering elements, command queue, fence, fence value, and fence event. Include device utils at the beginning of the file, compile and run the application. Which shows a Windows screen running DirectX 12, where the back buffer gets cleared in cornflower blue color and the Windows events like resizing and closing are handled.